All right. Thanks for tuning in. It's been a long time since I've done one of these. Today, I'm going to be going over how to port a very simple Fortran application over to GPU hardware using OpenMP with the AOMP compilers that come with ROCm. Before we dive into code, I just want to make sure everyone's on the same page when it comes to just understanding GPU hardware and GPU accelerated system here. So I've got a few slides for us to go through to start, and then we'll get our hands in code. This is a conceptual diagram of a very simple GPU accelerated system. We have one CPU socket here on the left, and it's connected to a GPU. Now, traditionally, this was connected over a PCI bus. You'll often see this be called the PCIe switch. Of course, there's other types of hardware nowadays that can connect CPU to GPU, like the Infinity Fabric or NVLink and those kinds of things. But the basic idea behind a GPU accelerated system is that you'll have what you usually have on a compute platform, CPU and its own memory space. And then the GPU itself, it's got its own compute cores and its own memory space. And so this is usually the first hurdle that folks have to deal with when they're working on GPU accelerated systems, is you have these two distinct memory spaces to handle. And all the APIs that are available for programming GPUs, they give you some way to manage these two distinct memory spaces, as well as launching kernels, so subroutines or functions, to run on the GPU side. Now, another bit here, if we look inside of the GPU hardware, this is on the right-hand side of the screen, is a conceptual diagram of what's going on inside the GPU. Sort of at this macro level, so the larger scale picture up on the top right. You have the key components of that GPU are the command processor, the compute units, and of course that GPU RAM. Now inside each of those compute units, you'll typically have a collection of compute cores, or what has been traditionally called compute cores. There's vector and scalar registers. There's usually some type of high bandwidth cache, very small capacity of course, and typically another type of workload manager on top of that. So the key takeaway, things to take away from this are, one, you have two distinct memory spaces and you have to deal with that. When you issue instructions on the for things to run on the GPU, all those instructions are communicated over that PCIe switch. And when you move data between CPU and GPU, you have to cross this connection here. And this can be a sore spot for a lot of folks, especially when you're first trying to accelerate your code. You might get some kernels running fast, but moving data between CPU and GPU can overall get you a slowdown. And so we'll talk a little bit about that today with the codelab walkthrough. Just wanted to throw a couple ballpark figures at you here. When we talk about performance of each of these components, we think about two things. One, you can think about, at least if you're on the compute units, so CPU or GPU, how many floating point operations you can do per unit time. And the other measure of performance, especially if you're in that bandwidth limited regime for your application, we talk about how much data you can move per unit time. So this is typically expressed in gigabytes per second. Now on most modern systems, the peak memory bandwidth you can expect between CPU and its own memory space, so that CPU RAM, is about 100 gigs per second. And between the GPU cores and GPU global RAM, it's about a factor of 10 larger. Now there's some caveats, of course. To be able to reach something like that, you need to be careful about your data layout and how you're doing your accesses in your GPU kernels. Now on that PCIe switch, the bandwidth between CPU and GPU, you can expect at least going one direction, so either copying from CPU to GPU, or the other direction, is order 10 gigs per second with the PCIe 3. PCIe 4, we're getting more into like the 32 gigs per second there, but generally order of magnitude about 10 gigs per second. So this, this connection right here, the PCIe switch, is by far the slowest point, or in this whole system. So if you're using this part of the hardware quite a bit, your application is going to tend to run slow. So usually the first thing, I try to tell people to do when they're porting to GPUs for the first time, of course, you want to get your kernels, your major functions and subroutines that occupy most of the time running on the GPU. And then your next plan of attack is to try to minimize when you're doing data copies. So ideally, you're only doing these data copies between CPU and GPU when you're doing things like file I/O, you're initializing your program, and you're really kicking things off. But even some of the kernels that they're not really compute intensive, because you want to move all your data to the GPU and kind of compute on everything there, you still want to get even some of your less important kernels over to the GPU. So that's all I wanted to talk about here up front. Let me shift gears and switch over to the code lab that we're going to do today. So if you look down in the description of this video, there's a couple links there. I provided a code lab link in case you wanted to follow along. Let's go ahead and switch over here. Okay, so I'm on a system here at our office. It's called Oram. Oram has 4 of the AMD's MI50 GPUs available. All of them are running there. Where we're going to get started today is downloading the repository, the Scientific Computing EDU repository. So we'll go ahead and clone that down to our system. So that's at Fluid Numerics, Scientific Computing EDU. And once you're in that repository, there's a samples directory. We're going to look at the Fortran samples and look for the smoother application. Now, if you did want to cheat and look ahead, there are multiple versions of that code. One is already offloaded to GPUs using HIP, one using OpenMP. So if you wanted just to cheat and take a look at the code, you could certainly do that. But today what I'm going to do is show you how we can go from a CPU-only version of this application and get it running on the GPUs using OpenMP. Real quick, just a brief overview about what this code does. So this code does a simple smoothing operation. It's very characteristic of what people would refer to as a stencil application. So it takes in a 2D grid of values, and then it does a sweep over the grid, or does a number of sweeps over the grid where it takes the average or a Gaussian weighted average of the like 9x9 blocks, or I think I have it configured right now to do the 5x5 blocks as it passes through the domain. But typically, especially if you're working on projects where you get a hold of some fresh code and you're tasked with porting to the GPU, sometimes it can be a little daunting to figure out where to start. This is a small application really to help you kind of get an idea of a general process you can apply to get yourself ported over. So what we're going to do first is demonstrate that we can build and run the code in its current form and get out some kind of output. And typically at this point you would ask the original author to tell you whether or not that output is correct. Or hopefully there's some kind of continuous integration in place to check that for you. But nonetheless, we'll start there. We'll generate some profiles to figure out the names of some of the subroutines that we want to look at. And once we do that profiling process, we'll transition over to the compilers that we want to use. So in this case, we're doing the OpenMP offloading. We're going to do this with the AMD flying compilers, which is really flying under the hood. So we'll make that transition, make sure things still run, and then we'll start our process to get things ported. This application, we've got a few files in here. There's a Makefile to build the code. There's 2 Fortran files, and yeah, there is a visualization tool here, but we're not going to look at that today. Let's take a look at that Makefile to start. So you can see by default, it's got the gfortran compiler There's no optimizations turned on to begin with, but when we start doing some of our timing, because ultimately we want to compare with what we do on the GPU, we'll change that so we can give, you know, this code some sort of equal footing in terms of how fast we can go on the CPU side. But we do have this -PG flag on, which if you used the GNU compilers before, you'll know that this is what we need to turn on so we can enable profiling, so we can look at this with GNU plot. Sorry, not GNU plot, gprof. Okay, so we'll just go ahead and run make. This will build the code. We'll take an ls here, so you can now see I've got two .o files. I've got my module file, so we know smoother is a Fortran module. We've got our object files, and then we now have an executable. Now I know this because I wrote the code. What the inputs are to this thing. Typically when you're trying to port to the GPU, you want to make sure you're working with a problem that's big enough. If you're not keeping that GPU busy, a lot of the performance metrics you'll get really aren't going to mean a whole lot. So this one's got a, you know, simple help interface here for us. So we have this application takes in 3 arguments. So nx, ny, which are the number of grid cells in the x and y directions. And then we have niter, which is the number of times we're going to do the sweep through the domain. So, you know, nx and ny, if you think about a smoothing application where we're doing stencil operations, you have a grid of values. If I increase nx, increase ny, it's going to increase the sort of problem size. So the cost per iteration will go up. And of course, the number of iterations, most scientific applications, right? We just do these iterative processes, the same thing sort of over and over. So we'll pick niter to be high enough to where we get enough time on the GPU to get some good sampling when we get there. But let's go ahead and just give this a run and see where we land. We'll take a look at the profile, and then we'll change some optimization flags. So I'm going to do smoother. Let's do 1,000 by 1,000, and we'll do 100. Hopefully this doesn't take too long. We'll let this go here. Okay, so we have a few things that were created during this process. So there's some output that came from the code. So this function.text and smooth function.text. There's also this gmon.out. That last file is something that was created so that we can do the profiling with gprof. If you haven't used gprof before, it's pretty cool. It's a completely command line based profiler. What we're going to use it for is to just look at the hotspot profile. So a hotspot profile is going to be it's an ordered list of functions or subroutine, and it's ordered by how much cumulative time you spend in a subroutine. So it'll tell you where your code's spending most of its time. This is great because we want to, obviously, if we're going to port to the GPU, maybe start with the most expensive routine. So the way we use this, we just do gprof, we pass in the name of the application that we use, or the path to that binary, and then we can pass it gmon.out. And I'm going to go ahead and pipe that output to gprof.text. And let me actually clear my screen here because I'm realizing that this is not showing up for you guys. So again, that's gprof. We'll do /smoother. So the path to that binary, and then gmon.out. Okay, and I'll go ahead and actually pipe that to a file like I was planning. So gprof.text. Okay, so now let's take a look at that gprof.text file. Up at the top, we see, okay, there's one routine we're spending 96% of the total runtime in. So that's an obvious target. Not all applications are like this. Sometimes I run into codes that have fairly flat profiles, and it's like, okay, just pick any of those. But here, this one's pretty obvious. We have inside of this smoother module, that's what this first part of that naming means, we have a method called apply smoother. So we'll take a look about, you know, how we're going to find that guy. And again, the point of me doing this with the simple code again is just to give you some tips and tricks and stuff on how you can start to like dig around in code, even if you've never dove into that code before. Okay, so we know to look for apply smoother. resetF is now occupying almost no time. So we might not worry about that right away. Okay, so let's take a look for this apply smoother just to get sort of a lay of the land here on what we're going to do. So I'm going to do grep with a -I to ignore case, because remember, Fortran's not case sensitive. And you know, if you're like me, every now and then when I write code, sometimes I don't always get the, you know, uppercase in the right spot. If I'm doing camel case, it can be a pain. Anyways, we'll ignore case so we can find that. And we're going to search all the F90 files. And you know what? I'm going to go ahead and turn on line numbering in that output. So we've got a call to that subroutine in the main function. We've got definitions. We've got a subroutine and end subroutine. So we know if we go into smoother.f90, we'll find that kernel there. So before we go into that, let's do a couple things here. I want to try to keep track of the runtimes that we have. I do want to give the CPU only code some fair advantage here. I don't know why I even have C flags in this. That's silly. Okay, we're going to go ahead and do this. We're going to do level 3 optimizations. Let's go ahead and clean things up. Let's make it again, and then I'm just going to run that application 1,000 by 1,000 with 100 iterations, and we're going to time it. I'm going to find something to take a note on. Keep track of that. Here we go. Okay, so we got about 3 seconds. So we'll say 3.73 is our runtime for the initial bit here. So 3.73 seconds. That's the time to beat for that problem. Okay, we'll see how we do. All right, so the next thing we're going to do, we do want to use the AMD Flying compiler ultimately for doing the OpenMP offloading. You can use Fortran for the OpenMP offloading, but you will have to install the GNU compilers from source and enable the OpenMP offloading for the AMD GPUs. That can take a while. It's a process, but it can be done. On this system, we do have AMD, the AOMP compilers sort of installed already, so that's what we're going to use. So to start, what I want to do is first, since the AOMP compilers are installed with ROCm, I'll set a variable for that. Usually ROCm is installed in the opt ROCm directory. So what we're going to do, yeah, set up this sort of default variable. If someone sets ROCm as an environment variable, you can override it in case you have ROCm installed in a non-standard location. And then the Fortran compiler, I'm going to hard set to ROCm bin AMD Flying. And let's make sure it's actually there before I do this. So if I looked at opt ROCm bin AMD Flying, it should be there. Okay, and it is. That's always encouraging. So let's do this. Let's run again. And now we'll go ahead and run that time again just to see where we're at with the Flying compiler. Okay, and we'll mark this time down as well. Okay, so Flying compiler is actually not doing too bad. So we got about 2.705 seconds. I guess there's a lot of things you can unpack from these little sorts of demos. Choice in compiler, choice in optimization flags, all these things make a huge difference in runtime. Just keep those things in mind. Okay, we're over to the AMD compilers. Great, we can do that. Now I want to talk about what it takes to actually build a code with OpenMP interpretation. So what I'm gonna do is shift gears here a little bit. Let me switch over to the slides. So this is the third page of that code lab that's down in the description in case you're following along. Let me zoom in here a little bit. So what I'm going to describe for you are things you can use for not just AMD Flying, but if you're doing OpenMP with C, C++, these sort of compiling steps will be needed. So generally there are 4 flags we need to set when you're enabling the GPU offloading with OpenMP. One is FOpenMP. So this is the flag just to enable interpretation of OpenMP pragmas. Let me take a step back, because I just realized I haven't talked about how this works. So OpenMP is interesting. There's 2, I guess, general classes of APIs to offload to GPUs. You have one where you can write your own kernels, you can manage your memory very directly, and then you have this sort of directive-based group where you insert in the comments of your code special comments that hint to the compiler about how to do the acceleration, and then the compiler does it for you. To enable interpretation of those special comments, which are called pragmas, you'll use this -f OpenMP flag. Now, there's more to it, because if you want to offload to a specific GPU, of which there are many different types out there, you need to set, which vendor you're using, as well as the target architecture code. So the vendor is going to be indicated by these two flags, so F OpenMP targets and the X OpenMP target flags, and then march is going to be set for the specific GPU architecture. So like if you've done things on V100s before, if you're an experienced GPU programmer doing things with like OpenACC or CUDA, the architecture code is going to be the thing you're used to. So you have SM72, for example, is for the V100s. If you're on MI100s, it's GFX 908. For the MI50s I'm using today, it's GFX 906. So what we're going to do is update the Makefile to add these flags for us. Okay, so we've done our bits with ROCm already. Now, the cool thing with OpenMP is you can offload to either NVIDIA or AMD GPUs. So we'll also want to include some some variables to set like paths to CUDA runtime libraries and things like that. So let's go ahead and dive back into the code here. All right, so what we want to do is add a few things here. So first, let's go ahead and bring that CUDA option in there, because I want to show you how you can use this to also build for NVIDIA GPUs. So we'll do a similar thing. Normally, CUDA's installed under user local CUDA. Okay, and then we're going to add a few flags down below. Whoops, I don't want the C flags in there. All right, so this is all OpenMP offloading. Okay. So the first thing we're going to want to do is get the GPU architecture. Now, ROCm does come with a binary called MyGPU, which if you're on a platform that has a GPU installed, it will detect what the architecture code is. So we're going to use that to our advantage, and we'll set that to a default. So the default for this variable will just be whatever comes out of my GPU. So I have this GPU arch, excuse me, we're going to run a shell command. We're going to run the we're going to run the MyGPU binary, and then this -d flag is for defaulting. For me, since my system is actually an MI50, I don't have an MI100 yet, or an MI200 yet, but since I'm building for the MI50s here, that's what I'll default to. And so now what I can do actually is, NVIDIA has this convention for their architecture codes where they always start with SM_. So if the GPU arch is ever SM_, I can set the values of those other two options, the F OpenMP targets, X OpenMP target. I can set those based on whether or not GPU arch starts with SM_. So again, you'll see me just kind of paste some stuff in here, but if you're looking through the code lab, you'll be able to see these. I'm going to walk through this line by line so you understand what's happening here. So we're going to do an if-EQ comparison. We're going to look for SM_. We're going to compare SM_ with the output of find string, where find string is going to search for SM_ in GPU arch. Find string, if it finds SM_, it's going to return SM_. If it doesn't find SM_, it's going to return nothing. And in that case, this would evaluate to false, and it would drop us down here. If it evaluates to true, then we know we're trying to build for an NVIDIA GPU. We'll set the GPU target, and this is kind of a mouthful, but if you're building for the NVIDIA GPUs, the F OpenMP target flag is going to be NVPTX64-NVIDIA CUDA. And when you build, you'll also want to bring in the CUDA runtime libraries. And this is why I brought in the CUDA definition up top. You do need to link into those when you build. Now, if you're building for the AMD GPUs, so in other words, we did not find SM_ in the GPU arch, you'll set the GPU target to AMD GCN, AMD HSA. So now that we have that defined, what we can do is append to the F flags now. So I'm going to go ahead and grab this out of the codelab and drop it in, and we'll again walk through it line by line. So we're going to do F flags plus equals. So again, we're appending to F flags. We're going to add that F OpenMP, so we enable interpretation of the OpenMP pragmas. We have F OpenMP targets and the X OpenMP target set to GPU target. Today, since I'm on an AMD system, this will evaluate to AMD GCN, AMD HSA. And then we have march is set to GPU arch. Now the cool thing about the way this is done in this Makefile is if someone were to set the environment variables for GPU arch for ROCm for CUDA, they could override all of those. So for example, if you do export GPU arch is GFX 906, for example, it's gonna use that target architecture. And this can be helpful, especially if you're on a system that does not have a GPU and you want to build for a particular GPU model. Okay, so now that we got that in, I'm gonna go ahead and clean this out and make sure we can still build. And it looks like we can. We'll get another runtime just because, well, we can. Shouldn't change much. I mean, there should be some statistical fluctuation, right? If I run it again, it's gonna dance around that 2.7 to 3.7 range. Not much has changed. Of course, it's not going to do anything yet because we haven't inserted any OpenMP pragmas. So now let's go back and take a look at what it is we were doing. So if you remember, we did that profile and we found that there was a method called apply smoother. Okay. When we did a grep for that, we found that apply smoother was defined in the smoother.f90 module. So we're going to go take a look at that and start offloading this to the GPU. I already forgot the line number, 89. Let's turn on that line numbering. There we go. All right, let's take a look at this kernel. Okay, so in this case, this is typical of some stencil applications. You'll have a tightly nested loop on the top here over I and J. So this is on 199. And then inside of there, this smooth F, it looks like we're doing a reduction. So we have smooth F is initialized to 0 at I and J. And then we say smooth F ij is smooth F ij plus, and we do a weighted sum sort of centered around that point ij. So we vary from minus NW to NW. So let's take a look. So remember the NX-NY1, we know those are controlled at the command line. We've said before that these, like at least for our demo, this is about 1,000. So we have 1,000 by 1,000 loop roughly on the outside, minus whatever this NW is, which looks like a buffer for doing these stencil operations. So we're not stepping out of bounds in memory. So let's take a look at what that NW is. If looks like it's passed in. So maybe it's defined in the main. Actually here, NW is 2. So if we go from minus NW to NW, so it's going to go from minus 2 to 2, that's 5 points in the X direction and 5 points in the Y direction. So there's not a whole lot of parallelism in that inner loop, right? We have 25 values that we're doing a reduction over. Not a lot to expose there. Most of the parallelism seems to be, in this case, at the outermost loop. So what we're gonna do here, one, because I can do this reduction for any ij independently of the other ijs, I'm gonna go ahead and parallelize these outer two loops. So when you're inserting pragmas for OpenMP, like there's a few things we need to tell it what to do. So one, we need to tell it what data needs to be copied to and from the GPU. We need to tell it, of course, then how we want to parallelize that region of code. Okay, so the first pragma we're going to do is what's called an OMP target. And this opens up a target compute region, or just a target region. This means that anything, so we'll close off down here with OMP end target. Here, line numbering back on. Okay, so basically anything enclosed inside of 99 and line 99 and line 115 we're telling the compiler we want to offload this section to the GPU. Okay, and usually on that opening of that target region is where you're going to want to specify what are called map clauses, MAP. Those map clauses are going to be used to indicate which direction we're going to be passing data back and forth. So we'll do OMP map target map. You can do, there's 3 different options you can put in here. You can put 2. Okay, we'll do map from, and then there's also map to from, which to from is the default. So if you don't put to from, it's going to assume you want to copy both directions there. So if you want to be explicit, you can. Now let's look at what we would want to do. And this is, if you haven't done this before, this it might not seem so obvious, but anything that's on the left-hand side of an equal sign for some kind of operation is going to be a write operation. So over here we have at line 108 smoothF, we're doing a write. And on the right hand side we're also doing a read, but it also looks like we're initializing that value up top. So because it appears on both sides, I'd be inclined to say we're going to do a map to from, because we're both going to read and write this value. The thing to be careful about here too is smoothF itself is an array from 1 to nx, 1 to ny, but we're only going to be updating values from 1 plus nw to ny minus nw and 1 plus nw to nx minus nw. So we're only updating a portion of that array. And if you're not careful, like what can happen in this case if I don't copy to and then also from, is those ghost values sort of on the border of your domain could get accidentally overwritten if you do a map to from and then you don't specify like the shape of the array. I'm going to do the safe thing here and just say, look, I'm going to do smoothF to from. I'm reading it, I'm writing it, and there's also some values I probably don't want to, accidentally overwrite because they're on the border. Okay, so smoothF is to from. Now, the only other variables that are used here are f and weights. Scalars, don't worry about them. You get them for free. They will be copied as needed to the GPU. So like nx, ny, and w, you don't need to worry about those. We have f and weights. They only appear on the right-hand side of an equal sign, so we're only reading from them. So we want to just copy f and weights to the GPU. So we don't need this from statement. We're going to do f and weights. Now, this is not enough to parallelize this region of code. What's going to happen if you just compiled this and ran this? It's going to be ridiculously slow, because what the compiler is going to do is generate code to launch a single GPU thread to run this loop. I didn't mention it earlier when we were talking about the GPU accelerated hardware, but a GPU's clock frequency, so the rate at which it processes instruction, is significantly lower than the clock frequency of a CPU. The reason a GPU can be faster is because it's got a lot more cores to do computations with. So, the CPU has maybe, order 10, 96 in some cases. A GPU's got thousands. So if you just run a single thread on a GPU, you're really not going to get anywhere. So this is where we need our next set of pragmas here. So we'll again start that line with a comment. So exclamation point for a comment, $OMP, which is the directive for an OpenMP pragma. And we're going to create what is called a teams or a league of teams on the GPU. So if you remember that picture of the GPU hardware I started off with, we had this like macro view of the GPU where you had like multiple compute units, and then inside the compute units there's a whole bunch of compute cores. So the league of teams, you can think of like, you're asking for that block of compute units, sort of, right? So we're going to do OMP teams. Again, this creates a league of teams, but the default number of threads per team is 1 unless we populate that team with multiple threads. So what we're going to do, what's called a compound directive. You'll see these a lot when you encounter do loops. We're going to do teams parallel, which is that parallel is what's going to get us multiple threads per team. We're going to distribute work to the teams. And then what kind of work do we want to do? Well, here we're doing some do loops. And the directive for that is going to be do. And if I just did do, it's only going to parallelize this outer loop. But if I want to parallelize both loops here, I need to do collapse 2. And what the collapse is going to do is it's going to indicate to the compiler, basically flatten these two loops out as if it were one long, massive loop. And that's the work I want to distribute across these teams. The only other thing we can do here is really give us some options to change how many threads we have per team. I'll go ahead and put that up there. Sometimes you'll see folks just do thread limit. You can do just num threads, and I'm going to set it to 256. The max value you can use for the threads is 1024, so 1024 threads per team. But this should do the trick here for us. So again, we've on line 99, we've opened up a target region, and then down below we've closed it. Okay, we've told it what data we want to move back and forth, and we said, okay, here's what I want to parallelize and here's how I want to do it. I want you to create a league of teams. I want you to give those teams 256 threads per team, and I want you to distribute these two nested loops to those teams to execute in parallel. So that's all we had to do. We're going to go ahead and save this. We're going to build the application. So we'll do make clean. Do a make, and hopefully I didn't mess anything up. We're looking good. And now let's go ahead and run that application. Okay. Now overall, we might not be doing too great. Actually, not too bad. 2.29. So I'll run it again here. Let's do that again. 2.3. That's not too bad. I mean, we're not significantly accelerated, and if you consider the fact that I was running in serial on a single core before, we really want to be doing better than what can be possible on, by fully subscribing the CPU cores. But we're getting a little bit better. Now, it's important to take a look at what's going on with a profiler. So I want to show you how to use rocprof to create a hotspot profile for your GPU kernels, and then we'll take a look at a trace profile as well. So let me pull that up here. So we're going to do rocprof. So rocprof is just a command line based profiler that comes with ROCm. We'll do ---- stats, which is going to generate our hotspot profile for us, and then we'll just pass it smoother. 1000. We'll give it the same parameters as before. So we'll take a look at that hotspot profile, and then I'll show you how to do a trace profile, and we'll visualize that Perfetto so you can see what happens over time on your on the code. So this results.stats.csv is what we want. This has the proof that we're running on the GPU. So we've got a kernel, smoother, apply smoother, right? And it's got some other stuff thrown in there from the compiler. But we're running our apply smoother kernel, and it tells us the amount of time in nanoseconds in total that we have up there. Okay, so let's take a look at, I like doing the trace profile because you can actually get the hotspot profile out with Perfetto. So what we'll do is instead of, actually we'll leave the stats in there, but if you add the sys trace flag, this will get a file out of this called results.json. We will download that onto our local workstation to get, oh, yeah, this happened before, I think. So the deal is some versions of ROCm, this will fail if the library, if your LD library path does not have the AMD HIP library in it. So if we just do HSA trace though, it should work just fine, because we don't have any HIP code in here, so we're okay. All right, so there's the, like I said, this is results.json file that we're interested in. We want to copy that down, so let me get my path here, and then let me go look up what the address was for this again, so that I can get this guy downloaded. Okay, I'm gonna go ahead and open up a new terminal, and we are going to, let's see here. I want a SCP, and I think my DNS was down earlier. So let me go find my Tell you what, here's what I can do. I can actually just hop off the node. There we go. And it's going to be that guy and then we're going to do this path. We're going to go ahead and download results.json. Oops, of course, I want to do it here. Okay, once that downloads, if I got my password right, we'll hop into Perfetto. Okay, so if you're following along, what I'll do, let me shift gears here one more time. So if you go to ui.perfetto.dev, I'll go ahead and drop that in the chat, ui.perfetto.dev. We can use this tool. If you have small enough trace profiles, you can visualize these online. Perfetto is available to run on a local web server on your own system, so if you have bigger files, you can do that too. We'll go ahead and open up a trace file. I'm gonna go home. Let me navigate to my spot here and grab the results file. So this was under Scientific Computing EDU, results.json. Okay. So what we're looking at here from left to right across the screen is a timeline. So here you see we've got 0 seconds, 0.2 seconds, 0.4, all the way out to the end of the execution. And then there are these 3 collapsible sections that show different types of activity. So the copy line is going to show activity for moving data between CPU and GPU. And then, of course, if you have multiple GPUs, this line here, so here I'm just showing one because I only ran on one GPU. It'll show the activity for kernel execution on that GPU. Okay. And so, like at a high level, what you can already see, because I've got some activity here, like showing up in the copy section, we have, like, there's definitely a lot of data copying happen, and we should expect that. We put those copy statements in our target regions. Then we've got our GPU activity. So if you click and drag over this region, you can get a hotspot profile of what's actually going on inside your code. So if I bring this up just a little bit, maybe I can make the screen a little bit, there we go, make the text a little bit bigger. We've got all these memory operations sort of eating up all this time up top. So AMD memory lock, AMD memory unlock, async copy, and then there's some overhead stuff for you know, waiting for kernels or waiting for these copy executions to complete. That's what these HSA, signal, wait, SC acquire, etc. mean. And then here, down here is our kernel running at 21 milliseconds, right? So 21 milliseconds for that kernel, but we've got all this time up above spent in memory operations. So like if we were able to get rid of that, we could be running pretty darn fast, right? Now, if you wanted to zoom in a little bit on this timeline, if you've done like computer games before, the A moves you left and right, D moves, so A and D move you left and right, W zooms you in, and S zooms you out. All right, if you zoom in far enough, you can see this activity. So you got async copy, here's my kernel launch, async copy, right? And all that empty space in between is still stuff running on the CPU because we're not, this trace profile doesn't pull out the CPU profiles. Okay, so with this in mind, like what we really want to do is get rid of these data copies. And you know, we know there's one other routine that's being called, and in fact, let's go back to our code. If I go back to the code and look at that main, oh right, I need to log back in. Goodness gracious. I'm gonna save that for later. Hopefully I got that password right. Come on, there we go. All right, we're back in Oram. So let's go into that. Let's go to samples, Fortran, smoother, and source, where we were. Okay. So if I had to go back into that main.f90 file, let's look for our apply smoother. There it is. So this is the main program that's being run. Here's our iteration loop. We're basically calling apply smoother and resetF back to back. Okay, we might be able to get somewhere here. Because basically everything else in this code is all like initialization, setup. We can ideally just move this stuff to the GPU once, do our 1,000 iterations, copy the result out on the other side and write the file, and we'd be good. So what we really want to do now is go ahead and offload resetF to the GPU. So we're going to kind of do the same thing that we did for apply smoother. We're going to also do that to resetF. So I'm going to cheat a little bit and copy these two directives. My advisor always told me if you don't learn how to cheat, you'll never be a good researcher. Little history, I guess, for you. Okay, so we're going to do a similar thing here. And again, because the buffer, like we're only doing this loop over the interior regions and not those ghost values, even though we're only updating F on the one side, what we're going to do is we're going to do smooth F2. Okay, I don't really need it to be copied back, but F is going to be to from. Okay, and I put this in here because it is a safe thing to do, to have these directives in here just in case OpenMP can't figure out what would need to be updated for this to happen. We'll still do our teams distribute, parallel, do, collapse too, because these are two parallel loops, and we're just moving data around from one place to another. No flops happening here, so all bandwidth limited. OMP, we're going to do end target for this region. Okay, let's build it again. Whoops. I think my GPU thing is not working correct on my system, so let's try that again. There we go. All right, so we built the application. Let's run the timer on it again. So we'll do 1,000 by 1,000 with 100 iterations. And let's see where we're at. So remember last time we got 2.29. Ooh, the timer went up. What's up with that? Let's run it again. We went from 2.29 now pretty consistently back up to 3.155. Okay. So let's see what's happening. Let's go ahead and get a profile again. When you don't know what's going on, always profile. Try to get as much information as you can. All right, so we'll do that rocprof with the stats flag for the hotspot profile. We'll do HSA trace to get the trace profile out. We'll run the same sort of parameters for our application. So you notice that none of this at any point am I changing these parameters. I try to be consistent with the problems I'm running. Okay, so let's take a look at the results.stats.csv. Okay. So now we've got both apply smoother and resetF, so that's good, but we're running slower. Sure, some of you out there already know the answer. What I'm going to do is I'm going to copy. Oh man, did I already forget it? Let's see here. Here we are. That's what I wanted. So I just didn't want to log out again. All right, and I don't need the PWD. I know the path. So we want that. We're going to download that results.json again. And pull that up in Perfetto. I think I got my password wrong. Darn. Oh, come on. There we go. All right, let's hop over to that other screen and reopen the Perfetto profile. So I just like go back on these. UI.perfetto.dev. open trace profile, and let's see, where did I download that to? Okay. Apps and Scientific Computing EDU. Okay, here we are. All right, so we opened it again. And remember, again, we're looking left to right is our timeline. We have the HSA API activity. We have our data copies, which, holy cow, there's a lot. And we've got some more GPU activity. So let's, again, we can click and drag over this region to see what's going on. We've got a whole bunch of async copy now coming in at 177 milliseconds. And then we've got our apply smoother resetF. So we still have a bunch of copies happening. So what is the deal? Again, if we zoom in, right? All right, so we got our copy, we've got apply smoother, copy, so things are going back and forth. We got another copy, and then resetF. So we've now just increased the number of copies we've done. But now everything's running on the GPU. So now we want to go ahead and get rid of this. The approach I'm showing you is very specific. Typically, like I encounter these applications where folks will have modules with subroutines that are used in like a lot of different spots. And if you don't do your OpenMP targets this way, what could end up happening is if you don't actually specify those map clauses, if they're not enclosed in what I'm about to show you, which are called target data regions, you can end up with some bad results. In fact, sometimes you just won't even have the right answer, or the code will just fail because it'll say the data is not present on the GPU. So what we're gonna do next is I'm gonna show you how to get rid of those copies without modifying these directives that we've already put in there. Like, we want to keep them in, so if someone uses them in another section of code but they forget to put a target data region around them, they'll still get the right answer. They just won't, have the best performance because they'll be doing data copies. Okay, so enough of that. If we remember, grepping around the code, we saw, hey, these kernels were defined here in this subroutine, and they were called from main.f90. So again, if we go in that main.f90, we've got this section here. So let's put that line numbering on again. So from 51 to 56, we've got these guys are being called here. So ideally what I want to do is open a data region here. So we want to open data region, and then here we want to okay, so let's just sketch out what we want to do. We want to open a data region. We want to copy data to the GPU. And I think that's all we need to do. Once we copy to the GPU, here what we want to do is copy data from the GPU. And if I look down below, I can see the only thing that really is of value is this smoothF array. This is the output from the code. So we got, okay, what we're going to do is copy smoothF out. And then we want to close that data region. Okay, so I'm going to show you how we're going to take those words and turn them into OpenMP directives. Okay, if you're following in that code lab, this is now on that 5th page. So using unstructured data directives, what we're going to do is have an OMP target enter data is the clause that we need to use to get this running on to get the data moved over to the GPU manually. So to do that, remember, we'll do comment $OMP. Here we have target enter data. So this is how you start a data region. And what really happens in the background is anything that's sort of executed between a target enter data and exit data for a specific variable, the compiler is going to generate instructions to keep track of the freshness of that data on the CPU and GPU side. So it makes a little bit smarter decision about when to move stuff. And in fact, in our case, it's going to see those map to and from clauses in our kernels, and it's going to be like, I don't need to copy things. You've already done it for me. And we'll show how that works by looking at the profile in the end. Okay, so we're going to do target enter data, and we're going to map Here, what we want to do is, you could do this in two sections if you wanted. You can do alloc. What we want to allocate is F, weights, and smoothF. Okay, so we'll open that region. And to close that region for these guys, we can do a target exit data. So we'll do OMP target exit data. And the map is still there, but instead of doing an allocation, we're going to do a delete. Now, if you're doing this in bigger codes, there's a couple rules to keep in mind when you're doing these kinds of clauses. The enter data alloc methods will always need to happen after the allocate statement. So if I did want to push it all the way up to the top of the code, I could, but it would have to happen after line 18 here, because that data needs to already be allocated on the CPU side in order for the compiler to know what the size of those arrays are, so it knows how much data to allocate on the GPU. So that's what we're going to do here. We've entered and exited, so we've opened and closed our target region. So now let's work on our copy clauses. So here we want to do, again, another OpenMP pragma. So again, exclamation point for comment, $OMP, and we're going to do target, update, and then here we're going to do 2. We're going to copy everything over, smoothF and weights. Now, I can do this safely here because I know F, smoothF, and weights have all been initialized to the values they need to be at this point. Then on the other side, all I want to do is OMP target update from. So from means it's coming from the GPU, and we're just going to copy smoothF back. Okay, so that's it. All we're going to do now is compile the code. So I've actually changed none of my CPU side code. So if I don't have the FOpenMP flag on, my CPU code is exactly how I left it. But I've now got these special comments in there that hint about how to get running on the GPU. All right, so let's go ahead and make. Okay, let's do that timing again. And now we're down a little bit further. So we got 1.433. Still a ways to go to really justify being on a GPU, but it's a darn good start. Let's now take a look at what's going on in that profile. So again, I'm going to copy. Oh shoot, I forgot to jump back over to the screen here. Let me walk you guys right back through what I just did. My apologies. Oh, no, I think we're okay. Nope. All right. Yeah, I'm going to walk you guys right back through that. Totally forgot to jump the screen back. Okay. So what we did was this OMP target enter data. I'll go ahead and turn that line numbering on to allocate F, weights, and smoothF on the GPU. As I mentioned before, what we need to do is make sure that these enter data regions happen after allocation. So again, after line 18 here. And then we went ahead and closed that target, that data region down at 67. So up here at 52, we enter data map. We're going to allocate F, weights, and smoothF on the GPU. So now there's GPU pointers for those. We did OMP target exit data map and deleted that data. So basically outside of this point, those pointers no longer exist on the GPU. And now we can manually control inside of that data region when we do the copies. And so anything inside of here, OpenMP makes some smarter decisions again about how to copy data back and forth. So we had 1, 2, 3, 4 pragmas that we inserted, and it's going to fix this problem here for us. Let me go ahead and rebuild that for you, and then we'll again run it. Okay. And again, we're down to that 1 second. So, you know, we only got about a factor of 3 with just a little bit of effort here. I mean, we spent maybe an hour on this. I do want to show you how, what this looks like in the profile at the end of the day. So let's go ahead and copy this down. And then we'll switch back to the Perfetto. There we go. All right, so let's go ahead and open up the trace profile again. So that still has copies. Let's go ahead and try this again. So let's go to apps, scientific computing edu, and results.json. So here we should be doing a little bit better. Looks like we still have copies happening. Yeah, let me see what's going on here. Because I did not do a profile, that would make sense. So let's go ahead and run under rocprof one more time. Again, using the --stats, --HSA trace to get our trace profile. We've got results.json here, which tells us, which has our trace profile on it. So let's download that again. Okay. Now that I've got that, let me reopen this and actually do this. There we go. That's looking much better. And so now you notice the order has changed on the left-hand side because now we're spending more time doing compute than we are doing mem copies, which is good. You want that to be the case for your code. And now you can see I've got copies happening up front, and then I've got my execution happening inside of here. So, you know, when I talk about this overall runtime, you'll notice there's this whole section up front, and it looks like it happens basically up to 0.75 seconds that, you know, there's just like a lot of stuff on the CPU happening. So if I really wanted to get a fair comparison of like speed up here, what I would probably do is run the code longer. So do a lot more iterations so that the time spent in iterations completely washes out this initialization stuff. The other thing I could do is if I take a look here, I mean, I got apply smoother is running at 0.15047 milliseconds. So let's write that down. 15047 milliseconds per call. So the average duration of the apply smoother method is 0.15 milliseconds. And then resetF is 0.04. We can go back into our profile with gprof and take a look at what those actually look like. So we can look at you know, comparison of the individual kernels rather than the total execution time. So let me jump back into the code here. So if we look at that gprof.txt that we started with, kind of interested. I'm on the wrong page here. Here we go. gprof.txt. So the average, so we had a cumulative seconds of 9.85. That doesn't seem right. Because I had, I did not have the acceleration on. So let's go ahead and turn off the OpenMP stuff and redo that profile. So make clean, make, great. And then I should be able to run the smoother again, and then we'll do another round of gprof. So we'll do gprof./smoother gmon.out, and we'll say gprof2.txt. Okay, so here we have 1.88 cumulative seconds. That makes a little bit more, self seconds, that's what I want. I want the 1.88 seconds, and I know I did 100 iterations, so if I divide 1.88 by 100, that puts me out at 0.0188 0188 seconds, which if I do that in milliseconds, that comes out to about 18 milliseconds. So 18 milliseconds on the CPU for a single thread on the CPU, so it's serial. 18 milliseconds compared to our 0.15, so about a factor of 10 faster for that kernel on the CPU, and that's that's more like what we want. So what this says to me is that like the GPU acceleration would definitely be worth it if someone were using this application for a larger number of iterations. Smaller problems, maybe not so much. That's all I have for you guys today. I do appreciate you tuning in. It's been a long hiatus since I've done these, so really appreciate it. If you like this stuff and if you want to drop comments in the chat, please, please, please subscribe to the channel. It only helps me reach you guys a little bit easier. Got plenty of cool stuff planned this year. Would love to see you next time. Thanks again for tuning in. See y'all soon.